Okay, welcome to lecture 2 of analysis of algorithms. So in this lecture, we will cover two main topics. The first one is basically big O notation. So in the previous lecture, we looked at the worst case scenario, the big O notation. In this lecture, we're going to look in detail at other asymptotic classes. And in the second part of the lecture, we will learn about two different algorithms. One is incremental and the other one is recursive. So we're going to look at these two different types of algorithms to solve a particular problem, which is sorting the elements of an array. Okay? So to begin with, just to recap and remind you guys of what we saw last time. So this is the definition of the big O notation. So the big O basically it's the upper bound of a function. So if we look here, if we take a function g of n, we multiply it by some constant. Okay, we need to find a constant in such a way that also starting from an n0, right, a particular size of the input data, then this function will always lie on top of our of the second function f. This means that f is in the order, okay, of g of n. Okay, so this is the common notation, and we call the g of n as the asymptotic upper bound on f, okay, within a constant factor. So here's something to recall, that in this definition, if we find a C, then that's fine. But this definition should not apply to every single C. So there exists. We can find a C that satisfies this, and then we can say that f of n is basically in the order of g of n. Okay? Now, we use big O notation to bound the worst running time, T of A. So T of A in this case, if you guys, by analogy, is actually our f of n, if n is the size of the input, okay, of an algorithm A. So let's look at this example. So this is quite simple. Now, what is the time complexity of this algorithm, guys? So it's in the order of n squared. Good. So it's quadratic, okay? So this one, it's in the order of n squared. Why we have that? So let's look at the first one. So how many times this will be executed? It's n minus 1 plus 1. So, and we have another additional number for exiting the loop test. So around n times. So this is always in the order of n, right? Because at the end, the constant, we know, does not matter, okay? And then we have these two nested instructions under the first for loop. So each of those will be executed at least n times, right? And then we have another second for loop. So in this instruction, now we look at it, right? We know that this is a for loop. It's not a normal constant instruction, so it's going to be executed n plus 1 if we add the exit test. So this is times. And then for this one, it will be times n, right? So at the end, we see that we need to look at the term with the highest exponent. In this case, it's n squared. It's not this n, okay? So it's in the order of n squared. Okay. Now, the running time of this algorithm is in the order of n squared. So you guys, now let me just recall, is n squared better than exponential or not? Is it better or worse? Which one is worse? If you have an algorithm with an exponential time, okay, complexity, and another algorithm with a quadratic polynomial time, which one is worse? The exponential, right? Because this is larger. So this is the upper bound. It's worse. But if we have, for example, a constant time, so this will be worse. Okay? Great. Now, today we're going to learn about time complexity classes, other classes. So far, we have looked at the big O notation. So this is, the big O notation, how we can graph it, right? So we're looking at the upper bound. We're trying to find an upper bound to our time, the time complexity of our algorithm, okay, approximated. Then there is another class which we call the big theta class, okay, so this is the average. It's the average time complexity of an algorithm, and this is how we graph it, so I will explain later on one by one for these two. And we have also the big omega time complexity, and this reflects the best time complexity that your algorithm can have. Okay, so we have worst, best, and in between we have the average. Okay, so let's look at first at the big omega. So here, so this is actually the best time complexity. How do we define it? So for a given function g of n, omega of g of n is actually the class of functions which satisfy, there exists basically a constant that is positive. So there exists, it means we need to find, if we even find a single number, one constant, then this applies. This, you know, like definition is true, okay? And also a positive number n0, right? Such that we have, okay, let me change. So we have basically c of times g of n is positive, and here we have less or equal to f of n. Okay, so this is actually what we call the lower bound. What does it mean? If you guys look at the graph, at some point we know this, we have the other way around. So for the upper bound, for the O, the big O, it's on top. For the omega, it's below it, right? So this is what we call the lower bound of f of n. So starting from an n0, we can see that f of n lies always above that function. So here we say that the omega provides an asymptotic lower bound on f, okay? So but beyond a certain n0, f of n never performs better than g of n, okay? So it never performs better than g of n. Guys, you need to revise those and wrap your mind around these concepts, okay? Now let's look at the other one, the big theta. So we looked at worst, big O, big omega, best, and now the middle case. So here, in this case, what we have, for a given function g of n, theta of g of n is the class of functions that satisfy basically this definition. So there exists positive constants c1 and c2, and a positive number integer n0 in such a way that now we have our fn sandwiched between these two functions. So it's bounded between them. And if you look at the graph, we have our function f of n. F of n is basically, it's bounded or sandwiched between these two upper bounds and lower bounds, okay? So we say that f of n is sandwiched between a gn constant factor, right? So in this case, imagine guys, if I am moving these two boundaries too close to f of n. So like basically I found two constants in such a way that it's too close. In that case, we can say that f of n is almost equal to g of n. And guys, remind me, when is this valid? Is it valid for n equal to, for example, 1? Or is it equal, like, is it, valid for n smaller than n0? No, right? So we're talking about asymptotic behavior. Asymptotic, it means when n tends to infinity, okay? So we're looking at the behavior of fn, okay? When n is very large, when the size of the input data is very large. So in this case, it's sandwiched, or it's bounded upper and lower by g of n. So in this case, we say that g of n is an asymptotically tight bound for f of n. And f of n, basically, it never performs any better than c1 times g of n, and any worse than c2 times g of n. Okay, so these are quite simple definitions. Now, we have some other cases. So let's just wrap before we look at the particular cases that are not commonly used. So, something to remember, for any two functions, f of n and g of n, we have f of n is basically in the order of theta of g of n, if and only if f of n has as an upper bound g of n and a lower bound g of n. Okay, so that's quite simple, and you guys can demonstrate this. Now, we have two particular also complexity classes, which we call the little o. Actually, I should write this as a small o. Let me just, the little o, okay, and the little omega, right? So these two classes are not very commonly used. So when you're guys going to analyze algorithms, we're mainly going to focus on these three classes, but it's good to know the other existing classes, okay? So these ones, the little o, basically, how is it defined? So let's look at this. So for a given function g of n, we have little o of g of n is the set of functions such that for every positive function, for every positive constant c, there exists an n0, a positive number or size of data in such a way, what we have here, let's look, such that this can be like f of n is greater or equal to 0, but it's strictly smaller than c of g of n, okay? So in this case, there are two, what are the differences? You guys, I want you to spot this. What are the differences between this definition of little o and the big O? There are two differences, okay? So in addition to small and big, that's quite simple. What are the two other differences? So first one, if you guys know this, before we did not have a strict inequality, right? It was like smaller or equal. And the second one is before we have there exists a C. So only one C would enable us to claim that this function is in the order of the other function. But for the little o, it's for any constant, for all positive constant. Whatever C you plug in here, this inequality should always be satisfied. Whatever C, you put 1, you put 1 million, you put 200, etc. Okay, you guys get that. So now let's look at these two examples here. So little o notation denotes an upper bound that is not asymptotically tight. So we call it the loose upper bound. Okay, it's quite loose upper bound. And let's look at these examples. So for example, 2 of n is always smaller than, it belongs basically to little o of n squared. Why is that? Because you can put any constant and you'll always have 2 of n strictly smaller than n squared, okay? But 2 times n squared does not belong to little o of n. Why is that? Now, it might seem a bit confusing, but you guys need to look at the definition. It means for every constant. This is true. It's not true, right? I can select C equals to 100. Oh, no, sorry, like smaller. Let's say 1. Sorry. So it does not apply. So this is not true. Now you guys can see how we apply. This is quite simple. Then we have n squared belongs to little o of n to the power 3 cubic, so basically polynomial. And then this one, of course, because of the strict definition, it's not also possible. So there is no graph, and if you guys look up books, there is no graph that actually demonstrate little o of n like we had graphed the 3 other classes. But what you need to remember that if we have a function f of n in the order of g of n, it means that g grows strictly faster than f, and we can multiply g by a positive constant c, and still beyond a certain n0, g will always exceed f, no matter what the constant we choose. Now, this is big O, little o. Now, on the other, like conversely, basically, we can have for the best case, we have the big omega. That's the basically the lower bound. Now, we have exactly the same definition, so I'm not going to detail this. So here we have for all constants, basically, this inequality should be satisfied. So this is strict, right? So in this case, what means that g of n basically is a lower bound that is not asymptotically tight. So it's a loose lower bound for our function f of n, okay? And you look at these cases, so n does not belong to a little omega of n squared. You guys can check all of those. Also, we have these different examples. N cubic also because of the strict inequality, so this is kind of a bit straightforward. Great. So these are the different classes. Now, you know how to, basically find or estimate the best complexity average and the worst complexity of an algorithm if we have the exact expression of t of n, which is in our case, like f of n, okay? The time steps of an algorithm. So things to remember, guys, here. So we say that f of n, if we compare all these notations, is in the order of little o of g of n if f is strictly smaller than g. So these things are to remember, okay? So this is a loose upper bound. We have the normal upper bound, which is the worst, and we generally use this one, okay, with like a relaxed inequality. Then we have the tight bound, right, with theta, and the lower bound, the best case scenario with big omega, right? And then what we have, the last one, is the loose lower bound with the little omega, okay, and strict, basically, inequality. Great. Now, it's important to learn how to compare these functions. Why? Because if we learn how to compare them, we can compare the time complexity of different algorithms. So let's say I give you a problem. Each one of you will come up with a solution. You compute the complexity of all these algorithms. And some of you will find that their algorithm is in the order, like let's say worst case scenario order of n squared or exponential or linear, and we want to compare them. So how do we compare these? There are some mathematical rules. So the first one, we call it transitivity. So in this case, you guys, it's kind of easy. So if we have fn in the order of g of n and g of n is in the order of h of n, what does it mean? So it means that we have, so fn and g of n and then h of n at some point, okay? So it means that f of n is in the order of h of n, right? So this is still an upper bound of fn. So basically the transitivity rule, we say it's transitive. So the big O complexity class is transitive. It applies, actually the transitivity rule does not only apply to the big O notation, it applies to all of them, to omega, theta, little o, and little omega, okay? Now, let's look at the second rule, which call reflexivity. So, guys, I will give you 1 minute to think about this. So, what complexity function notations are self-reflective? Self-reflective, it means if I write this, it's still correct. Fn, it's in the order of its own self, right? It's self-reflective. So which classes are self-reflective? Big O, yes or no? Yes, okay. Little o? No. Theta? Yes. Big omega? Yes. Little omega? No. Very good, so quite easy. And then we have another one. It's called symmetry. And this is actually, it applies only for the theta, right? So what does it mean? It's the sandwich function. So if we have f of n is in the order of theta of g of n, if and only if g of n can also be in the theta order of f of n. Why is that true? Let's look at these cases. Remember, guys, for these definitions, we only need to find a single constant that satisfies it, like these definitions. So for the first one, we have, this implies basically that we find a constant C1 times g of n such that it's lower or equal to f of n. And also we have the second condition. This is the sandwich condition, okay? Now, on the other hand, we need to find another function, okay? So this is from this side, such that C3 times Fn is lower or equal than g of n, and g of n is lower or equal than C4 times f of n. So, any suggestions of what C3 can be and C4 can be? It's quite simple. So here, if we compare these two guys, okay, and we take C3 equals to 1 divided by C2, then it satisfies it, right? So if we divide by C2, let's divide it. So here we have, or multiply by times f of n is smaller equal than g of n. What do you guys notice? That this guy right here is this guy, right? So it can be that way. This is just, to demonstrate that it is possible. And then the other way around, we can do it for this one, okay? So the last one is what we call the transpose symmetry. And the transpose symmetry applies to these different classes. So first we have f of n has an upper bound g of n if g of n has as a lower bound f of n. So this is quite intuitive, and it's like if and only if. So it actually goes both ways, okay? And also we have this for the little notations for the loose upper bound and for the loose lower bound. It's the other way around. So we call this the transpose symmetry. Okay, great. Now something to recall. So just to refresh your memory in terms of limit notations. So all these functions are asymptotically comparable. Basically, let's ask these questions first. Are all these functions or all existing functions asymptotically comparable? Any function you know in the world that you can ever create. Can we compare any functions when n tends to infinity? Mathematically speaking, no. Because, like it might not have a limit. It might, like kind of oscillate, right? So actually comparing complexities of functions, we need to, like the functions need to satisfy specific criteria. So this is not something that we can do for any algorithm and for any function, okay? So in terms of limit, if you guys want to, if you take the definition of the loose upper bound or also the normal upper bound, and you look at their definition in terms of the existence of the constant, and you make n tend to infinity. So what does this mean? It means like we have something like that, right? So if you divide by g of n, you'll have these different classes. So actually, mathematically, if we have the limit when n tends to infinity of fn divided by g of n, giving that g of n does not take 0 values, right? And the limit is 0, this gives us that actually g of n is a loose upper bound on f, okay? And which implies, we saw this before, if it's a loose upper bound, it's still an upper bound, okay? And here for the second one, if we have a constant, it means that actually g of n is an average bound or an asymptotically tight bound on f. And if we have the big theta, it means that if and only if we have these two. So we saw this before. And the last one actually is for the little omega, and this is actually, if you compute the limit and you find infinity, it means that g of n is actually a loose lower bound on f, okay? And if it's loose, it's still a lower bound, okay? So this is, mathematically, how can you define those? Great. Now, let's look at these also operations. How to add complexities. So if you have two functions, and you want to compute the worst, okay? So this is important. We guys are adding functions here, right? We're going to use all these operations all the time. So if we're adding them, what do we take? So the rule is if we're adding, you take the max. So this is for the big O. And we have exactly the same rule for the big omega and the big theta, okay? So it's exactly the same rule. We always take the maximum of these two functions, right? And now let's look at this example. What is the order of growth of this function or these two functions, n squared plus log n? N squared, right? Because it's the max, right? Quite simple. Now for this one, multiplication by a constant, we previously saw that if you multiply by a constant, it does not matter. So if you have a positive constant, you multiply fn by c, it's still in the order of f of n. So this is also quite simple. So all of these things are basically to remember. So you guys know that the constant does not affect either the best, worst, or average complexity. And for example, let's look at this. So we have order of 28 times n log n. It's still n log n, okay? Now, what about multiplying by function? So this is the new rule. If we have two functions and we multiply them, then it means we need to multiply their complexities, okay? And this applies to all the three big classes. So what is the time complexity for, these two functions like cubic and log n? It's log n. So you can plot this function and visualize it, okay? Cool. Now, let's remember very quickly, what did we do last time? So we filled in this table, right? This is the summation of the sum of different elements of this table. So I'm not going to go over this, but what was the complexity, guys, if you remember? What is the complexity, just if you look at this? So the highest term, all of these are constant. The only one that matters is n, right? And it's in the order of n, because this, these two statements will be executed at least n times. So you just screen and see, okay, the worst complexity here is in the order of n. Now, we're going to look at more complex statements, especially when we look at the algorithms later on, but this is just an introduction to how we compute complexity when we have an if statement, okay? So when we have an if statement, how we handle this in the algorithm. So we need to basically divide our, like when we compute the frequency, we need to consider two cases, the if true and if false. What if the statement is true? What's going to happen? How many times the statement will be executed? And what comes, what the instructions nested under the if, okay, test. And the if false. So in this case, I would like you guys to take a minute and try to solve it by yourself. Just think about it. Or 2 minutes. Okay, please write the algorithm on your sheet of paper and try to find the complexity. Here you're going to find two numbers, depending on if true and if false. Okay, so let's start with a simple case. So for this instruction, for the if test, it's a test, right? Since it is a test, we always need to perform it. We cannot skip it. So this instruction, it's nested under the for loop, right? So we need to execute it how many times? N times, whether it's if true or if false. Actually, we need to test it to know whether it is true or false. Now, okay? Now, what really is important here is what comes, like the instruction nested under the if statement. So, if it is true, it's always true, how many times this will be executed? N times. Good. And if it is always false, how many times? 0. We'll always skip it. That's it. Okay, so you guys get the idea. It's quite simple. Now, great. So just to wrap up, these are the different asymptotic classes. So we're going to look at, today we will learn about two particular classes, these two, the superlinear and the quadratic, or the logarithmic, the n log n and the quadratic classes. And this is something that you need to remember, okay, this order. Now you can compare them. You can look at best complexity, like theta. You can compare them in terms of, big O, big theta, big, also omega, etc. Great. So we're going to have a break in a little bit, but let me just explain what we're going to look at. Or maybe it's better to, okay, let's just explain what we're going to, the problem that we will solve. So we looked at different complexities, but we need to look now at algorithms and see how we're going to derive these complexities from different algorithms. So the problem that we want to solve is a sorting problem. So let's state it clearly. Remember, when you want to design an algorithm, first you need to articulate it. You need to write down what is the problem you want to solve. So here, given a sequence of n numbers, a1, a2, an, etc., reorder them or permute them such that all these numbers will be sorted in an increasing order. So we're going to flip them around and reorder them, okay? So what is a brute force or a naive algorithm that can solve this? So let's say I give you a random sequence like 25, 100, 2, okay, 10, 1, 7. So this is my sequence. These are the elements stored in my array. And I want to sort them out in an increasing order. So what is a naive algorithm that doesn't basically, it's like something that you can do right away without thinking and find the optimal sequence, sort out the sequence, which will give you this 1, 2, 7, 25, and 100. Any thoughts, guys? Okay, now you look at this example. I know I give you a few numbers, but imagine if you have I don't know, thousands, and you want to just use a naive algorithm, which is not a good choice to make, of course, but what can it possibly be?
Trying all permutations.
Yes, good. Trying all permutations, right? And then find the one that satisfies this condition, okay? So basically, try all permutations. And this is not good because we saw that actually this will give us something in the order of the factorial. So it's not something good. Right, so what we will learn then is we have this table and our goal is to think about the best strategy. How can I order it? How can I go and start ordering it? So it's, you're thinking, right? But you need to translate your thoughts into an algorithm. So maybe go, fetch the smallest one starting from one direction. So there are different approaches. There are many sorting algorithms that that were designed as solutions to this problem. And today we're going to look at two of them. One is called insertion sort, and the other one is called merge sort. Okay?